Marcus Webb was 51 years old when he retired from 22 years estimating structural materials for a regional contractor in Spokane, Washington. He understood exactly how load paths move through a corrugated arch, how steel conducts rather than resists, and how a building specification fails its occupants when the engineer never questions the geometry. He had $580. He had a quarter-acre parcel east of the city, paid off since 2017. The first contractor he called quoted $14,200 for a comparable footprint. The second quoted $17,800. He set both quotes face down on his workbench and started calculating. The Quonset form had been in his estimation file for a decade, a military-derived continuous arch with documented load and wind ratings that most residential builders had stopped considering. He understood exactly what the form could carry. What he did not know yet was that building one correctly required solving three problems that no contractor quote had ever included. Not one of them was structural. By the third week of April, Marcus had the panels on site. 14 corrugated galvanized steel sheets, 26 gauge, each 10 feet long and 3 feet wide, stacked flat on the graded parcel with plywood underneath to keep the edges clean. He ran a hand along the surface of the top panel. The ridges were sharp at the crown and smooth along the flat. The steel carried a documented yield strength of 33,000 pounds per square inch. He had read the product specification twice before ordering. The Quonset form is a continuous arch structure with documented origins in Second World War military construction. The engineering principle that makes it viable at low cost is the same one that makes an eggshell difficult to crush from the ends. Load applied to a continuous curve distributes along the full arc rather than concentrating at a single point. No ridge beam, no load-bearing walls. The arch is a structure. A 16 by 24-foot Quonset footprint built with 26-gauge corrugated panels carries a documented live roof load of 20 pounds per square foot under most rural county accessory structure classifications in the inland Pacific Northwest. Marcus had confirmed the permit classification with Spokane County's building department in February. Accessory structure under 200 square feet, $148. Process in 11 days. A neighbor named Phil stopped by the parcel on the second day of panel delivery. He looked at the stack and asked if Marcus was building a barn. Marcus described the footprint and the arch profile. Phil said he would not want to sleep inside something that looked like a culvert. Marcus said he understood and went back to the delivery receipt. The panels cost $312, delivered from a regional steel supplier 23 miles east of parcel. Anchor Hardware base rail and fasteners brought the structural materials total to $389. Solving the structural form had taken one afternoon of calculation, but the form introduced three separate problems that the structural specification said nothing about. Most builders who attempt a corrugated arch build discover all three of them after the shell is already closed. Marcus found the first one before the foam board was ordered. On a morning in early May, before any insulation was in place, Marcus pressed his palm flat against the interior corrugated steel at 7 a.m. The outside air temperature was 41 degrees Fahrenheit. The steel surface was colder than that, measurably colder. He held his hand there for 10 seconds and pulled it away. That is not an insulation problem. It is a geometry problem. Thermal bridging is a transfer of heat through a highly conductive material that bypasses the insulation layer entirely. Steel conducts heat approximately 400 times more efficiently than still air. In a Quonset structure, the corrugated ribs run continuously from the exterior surface to the interior surface without interruption. Every rib is a direct conductive path between outside and inside. When builders calculate the R value of insulation installed between those ribs, they calculate resistance through the insulation only. They do not account for the thermal penalty imposed by the steel ribs themselves, which short-circuit the insulation at every contact point across the full interior surface. Building science literature documents this effect as the gap between clear field R value and installed whole assembly R value. In a metal frame wall with R 19 fiberglass batts, the effective assembly R value can fall to R 12 or lower once thermal bridging through the steel framing is factored in. In a fully corrugated arch with no thermal separation between the exterior steel and the interior living surface, the degradation is more severe. On a 35 degrees Fahrenheit night, the unbroken interior steel surface of a corrugated shell can read 6 to 9 degrees Fahrenheit colder than the air temperature measured at the center of the space. Materials estimators call this the thermal penalty factor. Marcus had used the term in specification reviews for 11 years, calculating it into cost models for commercial cladding systems. He recognized the diagnosis the moment his palm came off the steel. The structure he had built his career reading told him exactly what was happening. The insulation he had originally budgeted would not solve it. Two things would, and neither one was what the original materials list had assumed. The practical application is this: a continuous layer of 2-inch polyurethane rigid foam board installed against the interior steel surface before any finish layer goes up. Not glued, not fastened, friction fitted directly into the corrugation channels and held in place by the geometry of the profile itself. Polyisocyanurate, documented in residential insulation specifications as polyiso, delivers an R value of approximately 6.5 per inch at moderate temperatures. 2 inches yields are 13 at the board face. More importantly, it creates a thermal break. The foam contacts the corrugation valley, not the rib peak. The rib peak, the conductive path, touches only the edge of the board. That interruption is the mechanism. Building science field measurement data shows that a continuous rigid foam thermal break layer reduces the interior steel surface temperature differential from the documented 6 to 9 degree F range to under 2 degrees Fahrenheit on the same 35 degrees Fahrenheit night. No adhesive required on the primary layer. Marcus cut each board with a utility knife and a straight edge on a sheet of plywood flat on the ground. The foam weighed approximate. He had spent 22 years calculating exactly this kind of material substitution, the point at which the correct product at a higher unit cost delivers a lower whole assembly cost than the cheaper product that fails on performance. The polyiso was that calculation applied to his own structure. A former colleague named Ray called and made to ask how the build was progressing. Marcus described a thermal break installation. Ray said he would have used spray foam. Marcus explained why rigid board outperformed spray foam in a friction-fit corrugated application. No professional insulation required, no cure time, no off-gassing in a sealed space. Ray said that made sense and did not argue further. Total materials for the full thermal break layer, $112. The surface problem was solved. But solving it exposed a second problem that had been building silently inside the sealed arch from the first night the door was closed. The first overnight was the last week of May. Outside temperature at midnight was 28 degrees Fahrenheit. Marcus had a thermometer mounted at sleeping height, 18 inches above the floor platform. It read 54 degrees Fahrenheit at 11 p.m. when he closed the door. He woke at 4 a.m. and checked it again. It read 47 degrees Fahrenheit. He held the thermometer at arm's length above his head, approximately 7 feet off the ground, near the crown of the arch. It read 61 degrees Fahrenheit. The air at the apex was 14 degrees Fahrenheit warmer than the air at the floor where he was sleeping. Air stratification is the vertical separation of air layers by temperature in any sealed space. Warm air, being less dense than cold air, rises and accumulates at the highest available point. Cold air settles at the lowest. Building science literature documents floor-to-ceiling differentials of 2 to 4 degrees Fahrenheit in standard 8-foot rectangular rooms under similar conditions, manageable and largely unnoticed. In a Quonset arch with a 10-foot crown, the geometry concentrates warm air at the apex with substantially greater vertical separation than a flat ceiling structure produces. Field measurements in non-rectangular sealed structures document differentials of 8 to 15 degrees Fahrenheit. Marcus had measured 14 degrees Fahrenheit on his first night. The thermal break layer had worked as designed. Interior steel surface differential was under 2 degrees Fahrenheit. The insulation was performing correctly. The problem was not the walls. The heater was not the problem. The ceiling was. Ray called again 2 weeks later. He had heard about the stratification reading and said the fix was straightforward. A larger propane heater would push more warm air into the space and raise the floor temperature. Marcus explained why that diagnosis was wrong. Adding heat source capacity does not address vertical separation. It warms the apex further while the floor remains cold. It treats the symptom, not the geometry. Ray said he would not have thought of it that way. Two responses to the stratification problem existed, one mechanical, one passive. Neither was what most small structure builders attempt first, and neither one was a larger heater. In early June, Marcus extended a tape measure from the floor platform to the interior crown, 9 feet, 11 inches. He made a note and set the tape down. The fix is called the arch circulation protocol. It requires mounting a small DC fan at the apex of the structure, angled to push air down the interior curve of the arch, not toward the occupant, not toward the floor directly, but along the surface of the steel itself, not toward the occupant, away from him, along the wall. This is the most counterintuitive move in the entire build. Every instinct about heating a cold space points toward directing warm air at the person in it. The arch circulation protocol points warm air at the ceiling. The mechanism is why it works. Warm air stratified at the apex does not need to be generated. It is already there. The fan pushes an accumulated warm layer down the curved interior surface, which acts as a distribution channel. The same geometry that created the stratification problem becomes a delivery system for solving it. The air follows the curve, loses elevation gradually, and re-enters the living zone at floor level without the velocity of a direct blower. Marcus has spent 2 decades reading airflow specifications for commercial HVAC installations. The principle was not new. Moving air along a curved interior surface to equalize stratification appears in building science literature as displacement ventilation, a documented method used in arenas and atrium buildings where vertical temperature differentials would otherwise make the occupied zone uncomfortably cold. He recognized the mechanism the moment he mapped it to his own footprint. He selected a 12-volt DC fan rated at 120 cubic feet per minute, mounted at the crown on a simple steel bracket, 2 self-tapping screws into the foam layer. Total hardware cost, $31. Running the fan continuously draws approximately 0.5 amps, under $1.80 per month at standard residential rates. The floor-to-apex differential dropped from 14 degrees Fahrenheit to under 3 degrees Fahrenheit within 40 minutes of the first test run. The circulation protocol solved the temperature distribution problem. It introduced a secondary consequence he had not fully modeled. 3 weeks after the fan installation, Marcus ran a finger along the corrugate. The fan had moved air through the interior as designed. It had also increased the rate at which warm, humid air contacted the coldest surface in the structure, the steel base, where the curve reached the ground and the thermal break layer ended. Condensation had been forming there nightly and wicking into the gravel subfloor beneath the platform. Ground vapor transmission is a continuous and documented process. Unconditioned soil releases moisture upward regardless of season. Without a physical barrier between the soil and the interior airspace, that moisture migrates through any permeable floor assembly. Building science field data records vapor emission rates through bare soil at approximately 3 to 5 grains of moisture per hour per square foot under typical inland Pacific Northwest conditions. In a 384 square foot footprint, that is a measurable continuous moisture load entering from below, and in a Quonset arch, it reaches the coldest available surface, the base steel, and condenses exactly there. The fix is a 6 mil polyethylene vapor barrier across the full floor footprint, lapped 12 inches up the interior wall base on all sides, and sealed at the lap with acoustical sealant. Not tape. Tape loses adhesion below 40 degrees Fahrenheit and fails silently across a single winter. Acoustical sealant remains flexible and bonded below zero. Total material cost, $38. Ray came by the site in late June to see the finished interior. He looked at the plastic sheeting across the floor and said it seemed like a lot of material for a subfloor nobody would see. Marcus explained the vapor pressure gradient and what the base steel had been collecting nightly before the barrier went in. Ray was quiet for a moment. Then he said, "I would have put rugs down and called it fixed. The barrier solved the floor. It could not solve the cuts." On a cold night in October, outside temperature 29 degrees Fahrenheit, Marcus stood at the door frame of the finished structure and held a lit stick of incense near the seam where the frame met the corrugated steel. The smoke bent inward at every corrugation peak around the full door perimeter. Steady, slow, continuous. The third problem is called the penetration seal failure, and it is the most overlooked thermal weakness in any corrugated arch build. A corrugated profile cannot contact a flat door or window frame along its full perimeter. The geometry prevents it. At every corrugation peak, a gap exists between the curved steel and the flat frame face, running the full height and width of the opening. On this structure, one door, two windows, that added up to approximately 14 linear feet of unsealed gap at penetration edges. Building science literature on metal shell structures documents these perimeter gaps as a primary infiltration path in an otherwise well-insulated corrugated assembly. Insulation behind a wall's surface cannot compensate for a continuous air path at the frame edge. The two-component fix, closed-cell backer rod, size of frictio. One additional requirement applies to any structure using a propane or wood-burning heat source inside a sealed metal shell. A carbon monoxide detector mounted within arm's reach of the sleeping position is not optional. Documented incidents involving CO accumulation in small sealed metal structures with restricted exhaust paths appear across cold climate safety records. The detector costs $17. Mount it. Test it monthly. The three methods do not operate independently. The thermal break layer addresses what the steel surface conducts. The arch circulation protocol addresses how air distributes within the sealed space. The penetration seal system addresses what the shell emits at every cut edge. Miss any one of them, and the other two cannot fully compensate. In November, outside temperature at 24 degrees Fahrenheit, Marcus sat inside the finished structure at 9 p.m. and read the thermometer at sleeping height. It showed 61 degrees Fahrenheit. The fan ran quietly at the crown. The door frame showed no incense movement. The base steel was dry. The complete three-method build cost broke down as follows. Structural materials, panels, anchor hardware, base rail, fasteners came to $389. The thermal break layer, 2-inch polyiso across the full interior surface, cost $112. The arch circulation protocol, fan, bracket, and hardware added $31. The vapor barrier and acoustical sealant cost $38. The penetration seal system across all three openings cost $22. The CO detector cost $17. The permit cost $148. Total, $757. Not $580. $757. The $580 figure had been the materials sealing before the permit and the safety equipment were factored in. The build cost more than planned. It cost $13,443, less than the lowest contractor quote. The difference between those two numbers is not a coincidence. It is the cost of understanding what three problems were actually doing inside a corrugated arch, rather than paying someone who had not diagnosed them to build around them. The structure operated through one full winter and one full summer. The coldest documented overnight was 17 degrees Fahrenheit. Interior temperature at sleeping height held at 58 degrees Fahrenheit on that night, with no supplemental heat running. The following April, Marcus ran into the contractor who had given the original $14,200 quote at a steel supplier east of Spokane. The contractor asked how the build had gone. Marcus told him the final cost and the thermal performance figures. The contractor was quiet for a moment. Then he said, "That's not a budget build. That's a diagnostic build." What Marcus constructed was not a compromise. It was an engineered response to three specific failure modes that corrugated arch structures present and that standard small structure builds do not address. Thermal bridging through a continuous metal shell, air stratification in a geometry that concentrates warm air 14 degrees above the occupant, and infiltration through every penetration edge that a corrugated profile cannot seal flat. Each problem had a documented mech.